Chemistry is quantitative. We take measurements of the properties of matter to determine composition. We measure how these properties might change over the course of a reaction. We use our measurements to design new chemical systems and technology. With this in mind, one of the most important skills you should develop in general chemistry is the ability to take good measurements and use those measurements appropriately in calculations. Every measurement has two parts, the number and the unit. The unit tells us the property that is being measured and the scale being used to measure it. For example, when we see degrees Celsius, we know that we're looking at a measurement of temperature using the metric scale of Celsius. The number tells us the magnitude of the property we're measuring relative to that scale, and how precisely we know that magnitude. We'll look at both parts of a measurement in more depth, but we'll begin with units in this PowerPoint. In chemistry, we use the metric or international system of units. This is often abbreviated SI. Here are some of the most common properties you will measure and their associated units. The magnitude of each of these basic units is defined relative to a standard measurement. For example, the standard kilogram is the mass of a cylinder of platinum iridium alloy kept in France. Any object with the same mass as that cylinder has a mass of 1 kilogram. This is a picture of a replica of that standard kilogram. It's kept under glass to try to prevent contamination over time, which could result in a change in the mass of the cylinder. The other standard units are all based on physical constants that should not change over time, like the speed of light in a vacuum or the excitation frequency of cesium atoms in a cesium atomic clock. In the metric system, each of these base units can be modified by a prefix, which can magnify or reduce the size of the unit by a power of 10. For example, 1 kilometer is 1,000 meters. Another way of stating 1,000 in exponential notation is 10 raised to the power of 3. Attaching the prefix kilo to any of the base units, be it meters, grams, seconds, or whatever, allows us to scale that base unit up by a factor of 1,000. Other prefixes allow us to scale the unit down. For example, a millisecond is 1/1000th of a second. In exponential notation, this is 10 raised to the -3rd power. This is a list of the most common prefixes and their powers of 10 that you will be expected to know. Our base units can also be used to derive other measurement units. For example, measurements of volume can be derived from using geometric formulas and length measurements of the dimensions of any regular solid object. Here are just a few volume formulas that you may remember from geometry. The standard volume unit is based on the dimensions of a perfect cube with sides of exactly 1 meter in length. According to the formula for the volume of a cube, you simply cube that length measurement to get volume. Here's the key to doing calculations with measurements. The units multiply, divide, subtract, and add as well. So if I cube a measurement of 1 meter, I have to cube both the number and the unit meter. So the volume of a cube with 1 meter sides is actually 1 meter cubed. Another unit of volume that we commonly use is the liter. It turns out that the standard 1 meter cubed is pretty large. A liter is a much more manageable unit to use for most things. It's also based on the standard meter cubed. 1 liter is exactly 1/1000th of a meter cubed. An even smaller volume unit that we use frequently is the milliliter. A milliliter is exactly 1/1000th of a liter and 1/1,000,000th of a meter cubed. A very useful relationship to know is that 1 milliliter is equal to exactly 1 centimeter cubed, or cubic centimeter. The cubic centimeter, which is also abbreviated cc, and the milliliter are the most common units used to measure liquid volume in chemistry and medicine. We measure liquid volume in the laboratory using volumetric glassware like a graduated cylinder. Graduated cylinders have the volume scale, usually in milliliters, marked precisely on the side. We read the volume by noting where the bottom of the meniscus or curved surface of the liquid hits the scale. In this case, the meniscus falls between 21 and 22 milliliters. We estimate exactly where it falls between those two values. In this case, I think the meniscus falls about 21.6 milliliters. We can also use volumetric glassware to determine the volume of an irregular solid that doesn't have consistent dimensions we can measure, like the nugget of gold in this example. Since gold will not dissolve in water, we can drop it into a graduated cylinder of water and see how much the level rises. The difference between the initial volume of water in the cylinder and the final volume after we've added the gold is equal to the volume of the gold itself. This is known as volume measurement by water displacement. In this example, the initial volume of the water before we've added the gold is 17.1 milliliters. After the gold is dropped in, the water level rises to 19.8 milliliters. The volume of the added gold is simply the difference between this final volume and the initial volume. In other words, 19.8 milliliters minus 17.1 milliliters. This gives us 2.7 milliliters for the volume of the gold. There is one other derived unit you need to be familiar with. That is density. Density is defined as the amount of matter in a given unit of volume. Something with a high density has a lot of matter packed into a given volume. Something with a lower density has very little matter in the same amount of space. The formula for calculating density is the mass of the substance divided by its volume. Say that we wanted to calculate the density of the gold nugget from the last example. We would take the mass of the gold nugget measured on a balance and the volume that we got from our water displacement calculation and plug that into our density formula. 51.842 grams divided by 2.7 milliliters gives us 19 grams per milliliter. Notice that the unit for density shows both units for mass and volume. This is another example of how units interact when we perform calculations with them. One last point about density. It's an intensive property. This means that its value only depends on the identity or composition of the substance, not how much you have. For example, I can take 6 different samples of gold, each with a different mass and a different volume. The larger the sample of gold, the larger the mass and volume. Now, when I calculate the density for each of these samples, simply by dividing the mass by the volume, I always get the same result, 19 grams per centimeters cubed. This holds true for every sample of gold I could measure, as long as it is a sample of pure gold. Intensive properties like density can be used to help identify what a substance is. So in summary, all measurements have 2 parts, the number and the unit. The units indicate the property being measured and the standard used for measurement. Units in the metric system can be made larger or smaller by the use of prefixes. The prefixes are all based on powers of 10. Derived units in the metric system include volume and density. Density is an intensive property that is linked to the identity or composition of a sample.